The problem that the safety industry currently has is that they started the single core processors, and now multi-core processoring are moving into the embedded market. This is a little bit a problem to the safety standards, because for now they didn't allow multi-core, and there is this new CAS32 standards, and this CAS32 standard now allows, under certain circumstances, to use multi-core in safety and especially in avionics. So what is the problem? The problem is that you need determinism. And determinism does not mean that an algorithm provides the same output based on the same input. It also means that the algorithm is finishing in its allowed time frame. With PikeOS, you can set up time slices and assign them to applications. But how you can make sure that an application does finish within its time slice, and this is what you need to do. It's called the worst case execution time determinism. In the past, this had been done with single cores, and you had to consider the number and bandwidth of interrupts, the scheduling behavior, the priority settings, and the memory controller and bus access, as well as the cache settings, which means when you access memory, the hardware plays an important role in the time that your algorithm actually needs. The problem is complex, but in the past, the industry has learned to solve it by usage of static and dynamic code analysis. When you have multi-core, the problem gets out of bounds because you have interference between the processor cores. That is because most multi-cores are implemented for average case timing and not so much for worst case. Even if this situation is rare, it may only happen once to cause a problem when a plane is in flight. So what do you need to look on the hardware level? So these are shared case, memory controllers, I/O, and anything that limits the bandwidth of the application to interact with its I/O and memory. As we will see, that these problems can be solved by cache partitioning and bandwidth monitoring. So here's a small table with some examples which can happen, which is the source and how to mitigate the effect. So on hardware level, one of the prominent things, except for example, bus controllers, is shared cache. So in this case, we are talking about L3 or L2 cache, which is being shared between the cores. Then sometimes, if multiple applications go into the kernel at the same time, you have to make sure that inside the kernel there are no locks. And finally, on application levels, that the access to shared resources is coordinated and set up in a way that it does not affect the overall performance and the worst case for each application. So we divide those problems into hardware-related things, application-related, and OS-related. Let's start with the hardware-related issues. So you can solve these things with cache partitioning and bandwidth monitoring. So cache partitioning is a software measure to mitigate the contentions, and this is done within PikeOS 5.0 by partitioning the cache via the PSP level on each platform. This needs support from the hardware and needs to be clarified by case, but on most PowerPC and ARM processor, this is available. And when it comes to RISC-V, this already is in by design by most RISC-V platforms. When it comes to applications, the advice to the customers on the architecture is to group critical applications with each other and let at the same time on multiple cores and run the non-critical applications also in parallel on different cores and do a cache invalidation in between them. So let's look at the examples. Here we have 2 cores in the time partition window tau 1. We run a non-critical partition and an application with a high impact on the cache. Afterwards, we do a cache invalidation, and then we run the critical applications in parallel. And from those, we know the exact behavior because those have been certified and investigated that they don't access the bandwidth or the resources or shared resources in an unwanted way, so that we don't have any interference between those applications at runtime. And the last one is operating system. So what we changed in PikeOS 5.0 is a way better resource locking. And this is called fine-grained locking. So on the left side, you see the standard behavior of older operating system and versions of PikeOS which were below 5.0. In this case, we have application A and B, and they are doing both syscalls. And in the very moment that syscall A is being processed, if application B now wants to execute a service, it has to wait until application A has finished, and therefore you get a worst case execution overhead for the application B. And you can see that those services in the kernel do not overlap, which means the other processor has to wait until the other core has to wait until the core run on which application A is running is finished. In terms of the fine-grained locking, which has now been implemented, you can see that the cores are actually working in parallel and that the application A does not lock the resources when it is in the kernel. That means that the application B can execute its kernel-safe services in parallel without any worst-case execution addition. So the fine-grained locking impact is quite clear. It means that as long as you do not access any shared resources, there will be no multicore induced conflicts inside the kernel. So let's look at the overview. So we talked about hardware-related issues and fixed them by cache partitioning. I did not go into the bandwidth monitoring because this is a very complex thing, and we will later see in the results from the Rapita tools that it is not really an issue if you follow the advice and set up the system according to CAS 32A regulations. In simplicity, very simple, if bandwidth monitoring is switched on, the access to memory and time of an application which does too much noise on the performance counter will be shut down and the critical application can continue undisturbed. On application side, we have to look at the architecture and make sure that only critical applications are running at the same time and that no shared resources being used. And on the operating system side, you can make sure that there is no interference when you use fine-grained locking. So what is the benefit? So with PikeOS 5.0, we can allow or enable our customers to build CAS 32A compliant airborne systems up to Del A right now. And the preconditions are fine-grained locking, cache partitioning, well-thought user architecture. Of course, you still have to do the static and dynamic code analysis, and this is where Matt will jump in.
So Oliver's already mentioned some of the problems with working with multi-core systems. I'm going to focus on the timing analysis side of things. We say that single core verification certification is a solved problem. We say this because we've been through certification. We've helped our customers go through certification with single core systems, and that's been going on for a number of years now. However, multi-core embedded processors have been available on the market for some time, but these aren't being fully utilized in the aerospace sector currently. As far as I know, there is no one who's gone all the way through certification with the FAA or EASA with a multi-core solution where all the cores are active. Some of the reasons for this are that the processors themselves are extremely complicated. They're often in the form of a system on chip where there are multiple buses and multiple ways of the individual components on the chip interacting. There is what effectively amounts to a network being implemented inside the chip with packets being sent around. But mainly we're going to focus on the contention for shared resources. So a multi-core system on chip has multiple cores, but it doesn't have independent main memory and independent buses for all of the cores. So some of the resources are per core, such as the level 1 cache, but then you may have level 2 cache, level 3 cache, which is shared between cores. You have main memory and IO buses that are shared between cores. And this means that what is happening on one core can affect the execution time of something happening on a different core. And this makes it very difficult to bound the overall execution time of the software. Also, with a multi-core system, the classical approach of static analysis for timing purposes is basically completely infeasible. The chips are simply too complicated to model to the required level of accuracy. And you have things such as temperature-dependent clock scaling, which is incredibly difficult to model. So there are mitigation strategies, which have been mentioned already, for addressing these interferences. The key thing is that these require verifying to make sure that they are working correctly. Another approach is to simply turn some of the cores off. That is something that is being done presently. Most of the extra certification required for multi-core systems does not apply for running single core on a multi-core SoC or running 2 cores in lockstep. But it is actually still important to verify that the other cores are not affecting the execution time. Recently, we've discovered that there is a difference between disabling cores altogether and enabling the cores but holding them in an infinite while loop. So we mentioned that robust mitigation strategies are required, and measurement-based analysis is required on the real hardware to get confidence that the strategies that we put in place are really working. All of this requires a strong ecosystem and cooperation between the various parties. At Rapita, we've worked with the SoC vendors to acquire in-depth technical information, and that's really important for identifying interference channels. Sometimes the interference channels are not obvious, so there are some obvious shared resources such as caches and access to main memory. But sometimes, for example, even with cache partitioning for shared caches, there are some common channels that all the cores go through. An example of this is the misstatus holding register, which all the cores need access to, even if their caches are already partitioned. We also work with the single board computer and board providers, as well as the operating system vendors such as SYSGO and the various middleware providers as well. So the RTOS offers these strategies for reducing interference. I wanted to emphasize that the interference is never fully mitigated. There is no magic bullet to turn off multi-core interference. However, we don't require it to be fully mitigated. We really require a deterministic and predictable timing behavior that we can use to demonstrate the software executes within its timing bounds. There's also a sort of implicit goal here with a multi-core system. If you were to, for example, move from a single core system to a quad core system, you're never going to achieve a 4 times improvement in throughput. However, if you were only achieving a 1.1 times improvement in throughput, then the whole process could be called into question. So there is an implicit goal as well to achieve throughput and computing power that is significantly increased compared to running in single core configuration. So we need to confirm the mechanism is doing what we expect it to do, and we still need to confirm that the application, when assembled as a whole, is still meeting its deadlines, and more importantly, provide evidence to convince a third party that that's the case. We're talking here about DO-178C, which is the latest guidance for aerospace. Oliver mentioned earlier something called CAS32A. So CAS stands for the Computer Authority Software Team, and they produced some guidance for how to comply with DO-178C with a multi-core system. Note that DO-178C is still the master standard that is that you're certifying against, and CAS32A is a set of guidance for how to comply with DO-178C. As the CAS itself has been disbanded, the guidance in CAS32A has been rolled into a new publication called AMC 20-193, also called AC 20-193 in the US. It's the same document under two different names there. And this inherited most of the content of CAS32A with some slight changes. We recently did a webinar discussing in detail the difference between CAS32A and AMC 20-193, so please get in touch if you're interested in this topic. But essentially the document provides a whole series of activities that the applicant must comply with, or can comply with, to demonstrate that their system is safe and is certifiable for DO-178C. So the Rapita approach to this problem, which we call MAC 178, consists of 4 strings. Firstly, we have our core tooling. All the RVS tools run on single core systems and apply to single core certification, but they're also used also can be used in a multi-core context. We also have engineering services, and these range from integration services, integrating our tools into a software and hardware environments, but they also include helping to design, run and analyze multi-core timing tests and experiments, as well as identifying interference channels, as I mentioned earlier. We also have Rapidemons, which is the first time we've mentioned that in this presentation. And the Rapidemons are interference generators, and we'll talk about those in a little more detail later on. And finally, we have certification artifacts themselves, as in templates and technical reports that we can help our customers assemble in order to produce the evidence that gets submitted at the end of the certification process. So in terms of the RVS tool suite, the key starting point is the Rapitest tool, which enables you to build a test scenario, define what the inputs and configuration of the software is, and it will build a test harness automatically and execute those tests on target. The key thing with Rapitest has always been automating. In order to certify a multi-core system, there are a great number of experiments and data that needs to be collected. So automating all of this process so it can run without manual intervention is key to achieving certification with the minimum cost for the customer. Rapidemons, as I mentioned, are the interference generating tools. They are small pieces of code that have been fine-tuned in order to generate the maximum possible interference per instruction executed. So they effectively represent the worst possible case of interference, and they are carefully tuned to both the particular interference channel, such as cache or main memory access, as well as the particular SoC or processor being used. And finally, because we are in the business of helping customers certify the software, the Rapidemons are qualifiable, as is the RVS tool suite. Finally, we also have the RapiTime tool. You can measure interference directly, and in fact, our tools are able to gather performance counters, such as number of cache misses, etc. And that is one way of quantifying how much interference is happening. But the way that really matters is the effect on execution time, because that's what we're trying to prove, that our execution time is within certain bounds. So RapidTime is a tool for worst case execution time analysis. It works on target, and it's been specifically designed for safety critical embedded systems. It concentrates on the worst case timing behavior in contrast to other timing tools which only focus on the average case timing behavior. RapidTime works on single core systems, but it also works on multi-core systems as well. And so it makes the ideal tool for actually measuring what is the overall effect of interference on execution time itself. And finally, I wanted to outline the process in a bit more detail. We start with the platform characterization. So this is understanding the hardware itself and how it behaves. To start with, we would run the RapidDemons in isolation. We can verify by looking at performance counters that the RapidDemons are acting as intended. They are generating the types of interference that they are supposed to be doing. And we can verify the slowdown against a known piece of code. You can also baseline the application code at this point against the RapidDemons in order to understand what is the worst case effect of interference on execution time. Secondly, there is an activity in software characterization, understanding the applications themselves. So we can fingerprint the applications using the data from the various RapidDemons that target different interference channels. And that will tell you which parts of the application are sensitive to interference across which channels. Some parts may, for example, be I/O bound, interfering with or sensitive to interference across input-output channels. Some might be sensitive to their cache being used and cache eviction. Some might be sensitive to main memory bandwidth, things like that. And this helps plan and schedule the application so that competing parts of the application don't compete unnecessarily for resources. We can run the application as a whole against the RapidDemons to verify what we're actually seeing in practice. And we can also verify the RTOS mitigation strategies and show that they are having the intended effect, and more importantly, that with the mitigations in place, the interference is within acceptable bounds. If you want any more detail about the process, please do get in touch. And finally, we have a demonstration for you of the PikeOS interference mitigation strategies and the RVS tooling running on a real embedded multi-core system. In this demo, we will be examining the timing behavior of a critical application running on the NXP T2080, which is running the SYSGO PikeOS real-time operating system. Rapita Verification Suite will be used to specify tests and collect on-target timing metrics. Firstly, let's explore the PikeOS setup, which is defined in Codio, SYSGO's development environment for PikeOS. In the Project Explorer, we can see Proc1, which maps to our critical application, and the other three processes, which map to RapidDemon contenders. Process 5 is our dummy non-critical application. Now, in the Rapita Verification Suite, we can see the integration we have set up for running timing tests and collecting timing data. Our tests are defined as JSON files, which you can see here. A new RVS feature scheduled to be released this year will allow you to use Rapitest's native test editor to build multi-core timing tests in a more visual way from the GUI. Let's take a quick look at the JSON file. Note the application of hardware event monitors that we want to measure, for example, L2 cache misses per thread. In our first scenario, we can see a baseline test with no contenders. In the other scenarios, you can observe a variety of different contenders running on each core. In Codio, we define that processors 2, 3, and 4 run on our spare cores, and our application of interest is running on core 0. You can define as many scenarios as you want to run different combinations of contenders and applications. In RVS, we have a number of configuration options available. In this instance, we are going to be using the metrics integration, which references the T2080 QDS integration. You can set up multiple integrations to easily switch between targets. For the run command, running on target, we are going to be using the Lauterbach Trace32 debugger to extract timing metrics. Depending on the metric entry that is added here, we will automatically generate the appropriate commands to be run in a CMM script. This script runs with Trace32 to set up the performance counter control registers in order to select the correct metrics to log. This means we don't need to produce any kind of kernel driver to do it for us in code, and only use what's available with the debugger. This approach ensures that we halt the target at a sensible point before we want to start recording the metrics information that we're interested in. The first PikeOS interference mitigation mechanism we are going to activate is L2 cache equipartitioning. PikeOS comes with a comprehensive platform manual which specifies how to use this technology. Back in Codio, you can see that L2 cache equipartitioning is now activated. The second mitigation strategy we are going to use to reduce interference is time partitioning. To demonstrate a system that does not have sensible time partitioning strategy in place, we have specified our critical application to run in the same time window as our RapiDaemon contenders. After that, our non-critical application runs on its own with no contention. For the purposes of comparison, we will now set up a more logical implementation of time partitioning. We will switch our critical and non-critical applications around so that our critical application now has its own dedicated time window. Our non-critical application that previously had its own time window now runs alongside the other contenders that represent other non-critical applications in a real system. You can see it's very simple to implement this change. Codio also makes it easy to see which core different time partitions are assigned to. The red box around the first item indicates that it is the synchronization core, so that is the master core that everything else is synced around. Now that we have specified our test and set up our interference mechanisms, we can return to RVS to collect real on-target timing metrics. We have selected a number of different instrumentation profiles and entry and exit points. We have finished our preparation stage, so now let's run our build. This will load our build onto the target, run it, and collect and process the trace. It will be repeated for all of the test scenarios we defined earlier in the JSON file. If we open up the Lauterbach Trace32 Power View, we can observe one of the test runs taking place. It will then let the target boot up into U-boot, download the PikeOS image, and do any other metrics capture configuration, and then instruct the target to run for the length of the test. We set a breakpoint on one of the RVS library functions which gets injected, called RVS output. When it hits this, the target will stop running, and then we'll be able to export the data from Trace32, which will appear in the trace list window. In order to capture the metrics information and timing information, we are actually doing a data write trace via the Nexus port on this particular board. That information is exported in binary format. We post-process the trace to convert it into the native format for RVS, which is a compressed trace file called an RPZ. After that, we can import the timing results into RVS. On the left-hand side of the screen, you can see the baseline test results where no PikeOS mitigation mechanisms were used. On the right-hand side are the results from the same tests, but with both L2 equipartitioning and an improved time partitioning profile in place. We can see that without the mitigation strategies, when we're running our final set of contenders, there is a very large increase in the execution time of our critical application. In contrast, the results on the right, where mitigation mechanisms are enabled, show a much more consistent execution time. There is still a slight increase, but it's a lot more consistent, and that will be a lot more predictable. If we click into RapiTime's Metrics tab, we can observe the results from our hardware event monitors that we specified in the JSON test file. We can use the filter feature to compare these metrics with and without RapiDaemon contenders present for both the left and the right-hand side results. We can then sort by metric so that they're all in sequence. The first entry of each set is the one without any contention. The entries below each event monitor are for the tests that did run contenders on other cores. For example, we can see the large increase on the final test scenario of 155% with contenders running compared to the baseline with no RapiDaemon contenders. Let's repeat the process on the right-hand side for the results that include PikeOS mitigation mechanisms. We can see that with both our mitigation strategies in place, we only get a 4.6% increase in execution time. Please note that PikeOS has other interference mitigation mechanisms, including bandwidth allocation management and fine-grained blocking, which are not explored in this demonstration.
Let's start with one from Raphael. And the slides of PikeOS showed bandwidth monitoring under partitioning strategies to mitigate intercore interference. Is it only monitoring, passive, or some kind of bandwidth reservation, for example, memguard? Oliver.
Yes. So first off is the monitoring part, and the monitoring parts on the clustering on the applications. So in case of the 228, the cores are clustered in the way that you can only measure the overall cache misses. That means that you have to guess a reasonable number for the critical applications, and then allow a level on which the non-critical application is allowed to add on that. And if this exceeds these threshold, then the non-critical application just does not get excess processor time, which means the time partition window of that application is not active any longer. Of course, you have to consider a certain threshold because still the critical applications are running, but effectively the non-critical application is either slowed down because it only gets every third or fourth window, or completely shut down depending on what it does. But usually the system are, let's say, designed that this does not happen. But since these applications are not certified, the outcome of those applications is not predictable. And so you must consider, or you must expect that they will, in the worst case, they will be completely shut down by not allocating or by not scheduling them anymore in the time partitioning machine.
Thank you, Oliver. I hope that answered your question, Raphael. We've got one here. Let me find one. Here's a good one for Matt. So this is from Stefanos. Thanks for your question. How is it possible to construct a RapiDaemon that generates the maximum possible interference when, one, it depends on what the other cores are executing, and two, the underlying microarchitecture details are unknown, e.g. hidden buffers, non-standard scheduling, service and replacement policies?
Okay, so first of all, just to clarify the claim I made in the presentation, the RapiDaemon is tuned to generate the most, for example, cache evictions per instruction. That's assuming, of course, that the RapiDaemon is being allowed to execute on the core. You're right that the overall interference does depend on what's happening on the other cores. We have done experiments that show that as you increase the contenders, so running against one contender on another core versus two contenders on two cores, three contenders on three cores, you're seeing an overall increase in interference. But we've also run experiments that show the opposite. And that really drives home the message that you really do just have to measure, verify all of your assumptions, and collect as much data as possible, because sometimes these SoCs behave in ways that on the face of it seem counterintuitive. To address the second point, yes, it does depend on what the operating system is doing. If you have any sort of bandwidth allocation mechanism in place, it may simply kill the RapiDaemon off. But that is, again, that's demonstrating that mitigation is appropriate. If you have non-standard cache replacement policies, that's part of the hardware analysis, and that would be taken into account in the design of the RapiDaemon. Obviously, we can only work with the information we have. So if there are hidden features of the SoC, then we would hope to discover those through experimentation.
Lovely. Thank you, Matt. Moving on to another for Oliver here. This is from Diego. I'd like to know if PikeOS and LinOS, sorry if I've pronounced those wrong, are POSIX certified or compliant RTOS?
So the base operating system, so maybe you remember those layering. So the PikeOS kernel and the system software have a very limited services, and per se, that level is not POSIX compatible. But since we have a virtualization solution, you can have a POSIX environment in your application. And currently, we are working on certified execution environments. So the PikeOS native, which is a subset of the C standard, actually is certifiable, and the POSIX is not completely. So there are parts that are being planned to be certifiable, especially in case of automotive and phase, but definitely not for Del A. So in case of Del A, you can still use POSIX on a non-critical applications, but for a critical application, you would use our PikeOS native API, which has, let's say, the most interesting parts, which you use for C. You don't have malloc, for example, because that would be dynamic behavior, but you can build it by your own if you really need it in the static memory that you have. And we have a certifiable math library, certifiable file system, and a certifiable IP stack, which is limited. But the good news is that you can combine those. So you can have a POSIX mid layer, which uses the certifiable IP stack in parallel to a POSIX, which uses the big LWIP stack, which has also TCP IP, and run in parallel a PikeOS native application using C standard stuff at the highest level. So that's possible due to the virtualization mechanisms.
Thank you very much, Oliver. So I've got another from Matt here that's just come in. This is from Aloise. You mentioned you discovered recently differences between disabling a core and running a while loop indefinitely. What are the differences? Did the disabled core generate interference?
I can't remember the details of which round it was, but it was something to do with, I believe there was a greater effect on execution time when the core was completely disabled versus when it was enabled and stuck in a while loop. And I think the reason for that was there were some accesses that were being made to the core that were timing out when it was disabled, whereas when the core was running, these requests and messages from other parts of the system were getting straight through and being answered.
Thanks, Matt, for clarifying that. Just to mention, we are due to finish in a couple of minutes, but we do have quite a few questions here. So we'll keep going and try to get through everyone's questions. So do feel free to stick with us, or if you need to go elsewhere, we do understand. But okay, we've got another for Oliver here. It's from Franz. What is the difference between PikeOS native and PikeOS SSW, and how do they interact?
PikeOS SSW is the PikeOS system software, and it's just the initialization layer. It's similar to the init process in Linux or systemd, but way much smaller, and it's the first application that is running in user space. This thing is not modifiable by the user, of course, because it's proprietary by the SYSGO, but its configuration is quite modular, so you can configure the partitionings. The PikeOS native itself is different. It's a library which is linked against your user application and provides the service that the PikeOS and the system software are offering. So the PikeOS native is a library which is linked to your application, and the system software is just the first application which is running run from the kernel in user space and which enforces the partitioning by configuration.
Thank you, Oliver. That makes sense. We've got another question from Raphael. It's quite technical, and I think it's one for you, Oliver. A second question about bus bandwidth. I assume time partitioning is there to prevent bus contention. If we could guarantee that the core running the critical application always wins when competing for the bus, could the system be certifiable without time partitioning?
So time partitioning just means if you have multiple applications or multiple partitionings running on one core, it makes sure that those partitions are running in a sequence. If you are using only one application per core, you could do this, but the time partitioning is still in the system because you cannot run any application which is not assigned to a time partitioning. So that's just a concept. In case of bandwidth allocation monitoring, we're using that mechanism just by switching off the scheduling of one time partitioning. So one time partition window. So you can use time partitioning in many ways. In a single core processor, all your partitions would run in sequence. And the major time frame is the entire cycle, and each application gets time in it. If you have multiple cores, you might want to have only one window per core. You can do that, but you still need this concept, because if you don't define a time partition window, the application just will not be executed. And also time partitioning, the bandwidth allocation makes use of it by just disabling the scheduling of a window.
Fantastic. Thanks for that, Oliver. So we've only got a few more to go now. So the next couple are for you as well, Oliver. From Andreas, does PikeOS support 64-bit architecture?
Yes, it does. Also, we have a list of PSP, which you can see on our website, and most of the recent architecture are 64-bit.
Thank you very much. And we'll finish with a quick one from Tobias, and that's: which CPUs are currently supported and BSPs provided from PikeOS for MPU?
Which BSPs? So we have the Xilinx UltraScale. In this case, we can build a setup with PikeOS and PikeOS for MPU at the same time. We also have, I have to look that up, to be honest. I think it's an R52 core, which we support. That is a space processor used in the Dahlia project. And apart from that, I really have to look into the BSP list. I know both. Due to the that the Xilinx UltraScale Plus board processor is used in many boards, we have a whole range of boards here that we support, even the new Korea and low expensive Korea boards.
Thank you. I don't think we expect you to know them all off the top of your head, Oliver, so no problem at all. And it sounds like the information's on the website if people should want to find out more. I'd just like to extend that one as well over to Matt, because I think the question of compatibility and hardware support is also quite relevant to RVS and the Mac 178 solution. What can Rapita support in terms of that?
Yes, so the underlying RVS tool suite, because we work at the source code level by injecting source code, injecting instrumentation, we can support any CPU that you have a compiler for and you're programming in either C, C++, or Ada. When it comes to RapidDemons, they are tuned to various architectures. We've worked with most of the PowerPC architectures, such as the T2040 that we looked at today, as well as the newer ARM cores, the A53s, A72s, such as you'll find on the Xilinx UltraScale. So the RapidDemons are CPU specific, but the RVS underlying tooling and the whole approach is completely independent of the architecture of the underlying silicon.
Thank you very much, Matt. There is just one more question. I want to make sure we get to everyone, and I'm not sure who it's to, so I'll leave it open to you guys who wants to answer. What about DO-178C, and also is this relevant up to DAL-A?
So I'll just jump in quickly and say that all the RVS tools are qualifiable for DAL-A projects if necessary.